Okay, so let's take a look at this function called name to point and try to understand it better. I think the previous example I went through it pretty fast, so I want to explain it again here. And I have a few boxes laid down in a grid, and I'm going to convert them into I'm going to name them using the assemble node. So this node is just going to add the name attribute, and I'm going to use the connect adjacent pieces to create a constraint network, or just think of this as a set of points that have a connection with the original mesh using an attribute. So I'm going to set this to points, and let's change this a bit. So this is my connection, and the only link between this geometry and this newly created geometry is the name attribute. Okay, and what I want to do now is I want to create a custom attribute on these guys, a color attribute in this case, and I want to copy this back into the mesh, into the original geometry. And so let's generate a random attribute, random from attribute. I'm going to use the name attribute, and let's delete everything except the points. And I have the point size set to 20. That's why I'm seeing them too big. And so we have 4 points on each box. Basically, each one of these guys have 4 points. You can see them in the center, and that's because of the connection. Okay, so what I want to do now is I want to copy this attribute, this color attribute, back into the mesh. The only link between these points, okay, or these guys, with the geometry is that name attribute. So what we want to do is, instead of copying the attribute using point ID or anything like that, we want to use the name attribute. And so the expression for that is the name to point. And what I want to do is I'm gonna use this original geometry, and I'm gonna import the color attribute respecting the name, and we're gonna copy that. So first thing, we need the point attribute. So I'm gonna call this point number, and it's equal the name to point. And let's take a look at this function. Actually, I haven't done that. Okay, so name to point is, I prefer to use the web because it's faster than using the local help. It's weird, but that's how it is. When running in the context of nodes such as Wrangle, this argument can be an integer representing the point number, starting at 0 to read the geometry from. So this automatically gives us back the geometry, the geometry or the point that has that same attribute. And the way the original core of this function is actually called find attrib val, and this function is a more generic version of the name to attribute, and we can use it to do lookups on other geometry using specific attributes. Okay, so but for this specific example, we're going to use this one because it's more perfectly suited for this example. So we want to import the geometry from the second input using the 1 integer pardon me, and then s at name, and so we have the point number now. Okay, and then we want to import the color. So cd equal point from the second input, and we want to import the cd, and the point number is point number. That's the information. Cool. So it's returning black, and the reason for that is because the name attribute here is a primitive attribute, and here is a point attribute. So all we have to do is to promote this guy to be the same type, and there we go. If I template this, you can see the name attribute is exactly copied, the color attribute is exactly copied from the points into here. And that's what we did in this example. Okay, we found the point number, and then instead of copying the color, we copied this attribute. Now what is this? What is this packed full transform, and why we're using this prim intrinsic function instead of using a point or a prim attribute? And if we go back to the packed primitives and middle click, there's no such thing. There is no attribute called packed full transform. And if we take a look at the documentation, intrinsic values are similar to attributes, but are computed on demand by Houdini rather than stored. So this is a different type of attributes that exist in Houdini. It's called intrinsic attributes, and they are not treated the same way as the normal geometry attribute. And to access these guys, we have to use this function called prim intrinsic, and then we give it the input name, which is number 1 in this case, and then the name of the attribute, and then the point number. It's exactly, think of this as point, okay? Exactly like that. But where is this name coming from? I don't see it anywhere. You know, if I middle click here, I don't see this guy. So if we take a look, at this, at the spreadsheet of the RBD object, or let's go back. Let's go here, and I'm gonna assemble this. I want it to be packed primitives, and if we middle click again, we just have path, nothing else. But if we open the spreadsheet, and the default view is this, and there is nothing here. But if we click on this list, you see there is a hidden attribute. There's all kinds of new attributes that exist only when the data is packed. And this is something Houdini does to be able to work with packed geometry. And if we display all of them, you can see they are grayed out, and this data is actually deferred. It's only computed or required or used when requested. It's not always there. Okay, so we have to do, if we need it, we have to do a request for it, and by default it pardon me, it's hidden. So I'm going to hide all, and this is the data that I need. It's called packed full transform, and this guy is actually a 4x4 transform matrix. Okay, and what we have in here is the transformation, rotation, and scale. And so when I import the RBD objects, okay, so this is my RBD object. If we do right click spreadsheet and go to under primitives and view this packed full transform, we're going to see the data change. Okay, so we're going to see that information changes there, and this contains the information about all these boxes. And by using this prim intrinsic function, we're importing this matrix, the 16 float matrix, this 4x4, into these points, into the constraint points, and then we're simply adding the multiplying the position with a matrix. Okay, and that's going to transform the whole, all the points, rotate them and everything. Now, apart from the transformation, we're actually getting something else. We're getting the rotation as well with these points, and I'm going to explain why we need the rotation in a bit. Now, I'm going to change one more thing in my setup to show you guys properly what's happening. Inside the connect adjacent SOP, I'm going to change it back to points, and now we have points in between the pieces. And let's go back to the geometry, and you can see the link, and if we hit play, I think we should increase the velocity. I want this guy to deform a bit more. So here, let's do it 40. Pardon me. Yep. Okay. So I wanted to get this this stretching to create gaps between the geometry. Okay, so let's go back here, and this is our constraint network, and this is the RBD objects. And if we transform them, you can see now that the constraint is actually a primitive, which we know, but now we're getting the stretching. So if I template this, you see we're getting this deformation It's the constraint is getting elongated because of this transformation. And so apart from the transformation which is being applied to all of this, we're actually getting transformation here, and that's coming from the full matrix, the 4x4 matrix, which contains scale, transform, and rotation. Okay, now let's do something. Let's go back here, and we're gonna let's untick this guy. I should have gone back to the first frame. Okay, so let's pick this up in the next video. We're gonna basically update, make a few changes so that the system retains the position, and we change bullets so it doesn't go back to the initial frame. But we'll resume from this file. Thank you guys for watching.